I'm Miss Will Simpson doing the portfolio for Module 10. So I'll get right into it and start with question 1, which was, what's the safety for working with acids and bases? How are they disposed of in a lab? So, as always, you should be wearing goggles, but that's especially important when working with acids because, as the video showed in the slideshow, acids can be really quickly to damage your eyes and vision, and this can be permanent, as it can dry out your eyes and many other horrible things to your eyes. To dispose, it's not just like water where you can just put it down the drain. Some acids are corrosive and could damage the drain and even end up harming humans. So you must dilute first, which means make thinner. So that can be by adding another substance, such as water maybe, just to not make it as strong as a substance. And then you have to put it in a bin specific for acids and bases that then can be disposed of somewhere that can handle substances such as acids and bases. So in those scenarios, should you be putting acids or bases down the drain, as this can cause a lot of harm. Question number 2 was explain the differences and similarities between acids and bases. Use a diagram or table to point out their key characteristics, create categories to assess them by. So I'll flip the camera here. So I'll be answering question 2, and I'll write a chart for the differences between acids and bases. So I have an acids column and a bases column over here. So first, how do they taste? Acids have a sour taste, and many people know how acidic lemons are, and that's kind of the taste that I put together when I think of sour and when I think of an acidy taste. And you also know how it feels if you get lemon in a cut or anything, how it stings. Now bases, they taste more bitter. So kind of the same realm of taste, but definitely a clear difference. Now acids are proton donors. Bases are proton acceptors. Now the opposite, as acids are electron acceptors. Meaning that they could get a negative charge. And bases are electron donors, which means they can get a positive charge. Next one I'll talk about is kind of what they do when they interact with something. So acids are corrosive, as I talked about before when I said what happens if, I think I spelled that right. No, I did not. Corrosive. If they go down the drain, they can burn and destroy materials, even metal, and especially skin or eyes, as I also said before. Bases are more soapy, so they're not going to cause too much damage, and they're going to look and feel kind of soapy. Now, something that I'll be talking about later is the pH level, or the pH scale. So acids will have a pH level lower than 7. And this means that they're very acidic and have a high pH level. Bases' pH level is always higher than 7. And now you can see that, so acids are below 7, bases are above 7, so 7 is a neutral. So yeah, those are the differences between acids and bases. Some of the main ones. There are others. So I'll flip the camera around again and answer question 3, which is how are they like ionic compounds, or are they ionic? So, acids are molecular compounds that dissolve in water to produce hydrogen ions in an ion. An anion, which is a little tricky to say. An anion is a negative ion. Bases are ionic compounds consisting of hydroxide ions and a cation. Now, a cation is a positive ion, so that's where they're different. Yeah, that's a pretty simple one. Question 4 is how do indicators work? And I will flip it back around so I can use my whiteboard again. So I'll be answering question 4, which is how do indicators work? And I was asked to look up 3 indicators used in labs and make a table of the colors they turn in acids and bases. So first, pH indicators work by detecting the presence of hydrogen and hydroxide. The way that the presence is detected is by creating reactions. So, all right, up here, indicator, and then color for acid and base. So, the first one I looked at was methyl orange. Now, when you see this, you might assume that there's one of the colors is going to be orange. And it's almost right. When this comes in contact with acid, the color is going to turn red, so close to orange. And now when it comes in contact with the base, it's going to turn yellow. Now, methyl red. You might think this is going to be similar, and well, you'd be correct. When methyl red comes in contact with an acid, it's going to produce the color yellow, so the opposite. It actually is the opposite. And then when it comes in contact with a base, you guessed it, it's going to turn red. The last one I looked up was thymol. This is a little bit of a longer one, so I have to pace myself. Thymol. Blue. And now this is a second change. I'll write it down here so I can fit it. Now, you might think there's going to be blue here, and you would be correct. When this comes in contact with an acid, it turns yellow, like methyl red. But now the difference is when it comes in contact with the base, yep, it turns blue. So that is question 4. So I'll flip back around to answer question 5. Question 5 is explain how the pH scale works. A few facts, and then tell me what happens to the hydrogen ion when you go from 3 to 6. So, a pH scale measures how acidic or basic a substance is. A substance that is neither acidic or basic is neutral, as I said before. So now on the scale, 1 at one end is very acidic and the most acidic you're going to get. And then at the other end, 14 is very basic and the most basic that you're going to get. So now, part of the question was what happens when you go from level 3 to level 6 on the pH scale. So the hydrogen atom becomes 1,000 times less acidic. And this is like in math when you do the power 2. So instead of doing, you multiply 10 times 3, which would be 30. It's not correct. You have to do 10 times 10 times 10, which is 1,000. So yeah, I'll now be flipping back around to answer question 6. So question 6 was I was asked to draw out the pH scale, find materials to represent a strong acid, weak acid, neutral, weak base, and strong base. So, get right into it. It's usually drawn in kind of a large rectangle. So I'll have to draw 14. 1, 2, 3, 4, 5, 6, 7. Oh, on track so far. 7's right in the middle. 8, 9, 10, 11, 12, 13, 14. Perfect. Fit them all in. See that? A little bit trouble seeing all that, so I'll just try to describe it well. So it goes 0, 1. So actually, I'll clarify. In the last clip, I said that 1 is the lowest. It's actually 0 is the lowest. And that's the most acidic that you can get. I was incorrect there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So, at 0, which is the most acidic, an example is a battery. Now this is a very acidic substance, has high levels of acid in the battery, and this happens for most batteries. Now something that's still acidic but not very acidic, milk. And I actually did not know this until I looked at this. I'm not a huge milk fan, but when I drink it, I don't usually think I taste acidicness in it. Now, number 7 is neutral. You might think, what do I know that's neutral? Or what do I think of when I think of neutral? I think water. Oh my gosh. Butchered that writing. Water is neutral here. Now, what is something that is basic but not very basic? I did not know this either. And this is kind of interesting. Blood is basic, but at the lower end. I want something that's super basic. Drain cleaner. Kind of boring one. Not like blood or anything. Now up at the top, I'll just draw to make it clear what's acidic, what's neutral, and what's basic. So we're here from 0 to 6. Line here. This is all acidic. Now number 7, water is neutral. I'll just write an N because I don't have enough space there. And then 8 to 14, basic. Wow, it's actually tough to write on this whiteboard. All right, so that is question 6. Yeah. So I'll be answering question 7, which is what is a neutralization reaction? Show this using a binary acid and an oxyacid. So a neutralization reaction is when an acid and a base react to form water and a salt. This involves the combination of hydrogen ions and hydroxide ions to generate water and salt. Or those two generate water together, as hydrogen's H, hydroxide's OH, so H2O. So I will be showing this by using sulfuric acid and sodium hydroxide. So 4 plus alright, so it's kind of like a double displacement, as was talked about in the last portfolio, where you're kind of switching. This was A, and this was C. You're kind of going to be switching those. So if you just look at it quickly without balancing, we're just going to get Na SO4 plus HOH. Now I'm going to go grab another color so I can draw the changes with coefficients and subscripts. So I'll be right back. I just need another color. Sorry about that. So, to balance this here, we figured out, is a charge of -2. And this sodium has a charge of +1. So we're going to need to put 2 of those to balance that out. And now over here, to balance this out with the other, so over here, on the first side, we're going to need to put that to make that balanced. And over here, there's 2 hydrogens over here. And now there are 2 hydrogens over here. So to balance this out, we need to put a 2 here. But that makes 2 hydroxide. So now over here, to balance that out, we put a coefficient of 2 in front of the sodium. So that there's a 2 over here. So that's balanced. And now these 2 are balanced. So we're all set there. And now this is a neutral. This was a neutralization reaction shown. Sorry, that last one was a little bit shaky. I'll now move on to the last question, question 8, which is, what happens when you put an acid with a metal? So, when acids react with metals, they produce a salt and hydrogen gas, as was shown before. But not all metals react with acids, however. So this won't happen all the time, but most of the time it does. It's about, I think I saw 75 to 25%. 75% is the times that it will react and create the salt and hydrogen gas, and 25 is the time that it won't. Thanks for listening. I'll put these all together, send you the link, and it will be all good. Thank you.